Hello and welcome to this lecture on moisture transfer in pores and also the concept of capillarity, which we will show by some examples of, yes, we're going to play a little bit with water and its absorption into some small pores. First of all, I'll start to drink a little water here. So I take a nice GTU water and I pour it into the glass here. A little bit, also I need to drink, so cheers. But the topic really is what you may know when you have looked deep into a glass of water. You can see the water surface is kind of curved a little bit along the rim of the glass. And if I put the glass here, perhaps we can see it, or otherwise you can test it for yourself next time you drink a glass of water, how at the perimeter of the glass, the water surface kind of bends up along the glass surface. And that is actually the effect of surface tension, the intermolecular forces we have in water and for the water molecules. So to start the lecture about it, we can see here on the slides we have the water molecule, which is a small molecule. It's a polar molecule, so it has some electrical intermolecular forces with other materials. So on the slide we see how the water molecules, how they interact within the glass, so the attraction forces from the water with the glass means that we have a drawing up of the water surface along the glass edge. So these intermolecular forces, the adhesion between the water molecules and the glass, mean that we have this drawing, so it acts like a tension force along the perimeter of the pore. That means that we will see some drawing up of the water, and also the water surface comes a little bit with a contact towards the glass at a certain angle, a contact angle theta, as we can see here. And for most building materials, they are hydrophilic, they like water, so they absorb water. But in some cases, we have repulsing forces, but that's not common for us to see. Then it's hydrophobic. Now, to carry on with the hydrophilic condition, or rather first we'll take a water surface without the material at first on this slide here. We have a plain water surface, and it is such that the pressure in the water, the liquid pressure, it's the same as the gas pressure that we have over the liquid surface. So this is the top of the water, the surface of water. The gas pressure, that's the atmospheric pressure that we have in normal air, you could say. So for such a flat surface of water, the liquid and the gas pressure around the surface are the same, no difference between the two. But in our glass tube or vessel, because of these intermolecular forces I talked about before, we have this surface tension, and we use the symbol sigma to indicate that, to draw the water up along the glass surface. And if we make a pressure or force equilibrium over the water surface, then we see, first of all, we have the liquid pressure times the area of the water. And if this is a cylindrical pore, you can imagine, then the area is pi times the radius squared. And then we have the liquid pressure, so that's the force pressing upwards. Downwards, we have the gas pressure, the atmospheric pressure, so that presses downwards. And what comes in between, that's the forces that are acting around the perimeter with this surface tension. So 2 times p and the radius, that's the perimeter length, sigma, and then cosine we must take to that contact angle with which the water touches the glass. So altogether, making up this, then we can see a difference between the liquid pressure and the gas pressure, which comes because of this surface tension. And also there's a strong relationship with the radius, which comes down in the denominator. The surface tension, we have a value here that we can remember when we're going to use it for calculations. So altogether, the capillary action, as we call it, meant by the surface tension, it makes an under pressure within the water below the surface. So that means that we have, when we talk about capillarity, we really mean that if we have such a pore, like a glass tube, then because of the under pressure, it's able to suck up water from a reservoir. And we can look to the forces again. At the top, we have that liquid under pressure with which we just before calculated how it sucks up the liquid. Down below, at the reservoir, we have a liquid pressure of 0, or rather, we have the atmospheric pressure. But this has to be counterbalanced with the gravity, so the weight of this water column with which the water has risen up into our glass tube here. So we can make again some balances. So looking to the force from below, the force from the top, the difference between those two has to be in balance with the force of the gravity. So this we can put numbers to. And now I'll talk about the capillary pressure rather than the liquid pressure. It's the same, only we have the gas pressure, the atmospheric pressure as the difference. And this difference between the capillary pressure below on the bottom and the capillary pressure in the top, that difference is what comes from the gravity distributed over the area. So that means that we can isolate what is the capillary pressure up here. Well, it's this formula here, 2 sigma times cosine to the contact angle and divided by the radius. So again, divided by the radius, remember that. Now, we'll make a little experiment soon. And for that, I'll take again such a glass vessel, and I would like to calculate how high we can have the water sucked up into the glass tube as it is. We take again the equation from the previous slide. So the capillary pressure can be calculated by this formula, the inverse proportionality to the radius. And we had from previous again, that's equal to the weight, to the gravity. And therefore we can isolate from gravity, we have the dependency on the height of the column here. So the height times the area and the density of water and the acceleration of gravity that gives us the force that the gravity works with, distributed over the area. So then we can isolate the max, x max as it's called here on the slide, so the height at which we can suck up the water. And we have this equation here, 2 sigma times cosine to the theta, and then divided by the density of water, acceleration of gravity, and the radius. So let's try to work it out. But just remember that this maximum height, it's inversely proportional to the radius of our pore. Now, I have with me today, I have a small glass pore. Here is my tube. And this tube has a diameter of 1/2 millimeter. So that means that the radius is, now I use SI units, so that's 0.025 meters. And then I could calculate the maximum height as I had it on the slide before. So X max we called it. So the height at which we can have suction of water into our tube here was 2 times sigma times cosine to that contact angle, and then divided by the gravity, or so, excuse me, the density of the liquid and the acceleration of gravity, and by the radius. So for this we can insert numbers. We had from the previous slide the sigma is 72.5 times 10 to the power minus 3 Newton per meter. I don't write the units, we use all SI units. Cosine to theta, but what is theta? We have not talked about that, but that was the contact angle we said. But what is it? What value can we assign? If we don't know anything better, let's assume that theta is 0. That means cosine to theta becomes 1. That's if we don't know any better, and normally we do not. The density of water, 1,000 kilograms per cubic meter. Acceleration of gravity, 9.81 meters per second square. And then the radius, and in this case, 0.0025 for my capillary. When I calculate all this, the result becomes 0.059 meters, or if you will, almost 6 centimeters. Now, let's make a small experiment to verify if the theory holds also in practice. And to make this experiment, I will use some pure water, distilled water. And I pour it into a vessel here. So we have a reservoir that we're making. I want to have at least 6 centimeters in my vessel here. So let's see how it goes. I think that would be sufficient here. Here is my tube. And what I do is that I put the tube into the water. Now the tube is dry. It might be a little bit hard to see. I will replace my glass from over here so you can see how it looks when it's dry, if there's anything to see, apart from a little bit some dirt perhaps. Let's see how it goes. I'll now put the tube here into the water. And now the water sucks up into the tube here. And let's see, I put my finger on top, and then let's see how much it has sucked up. To be honest, I can hardly see it, but let's see if we put it in front of here. It hasn't sucked up those 5.9 centimeters as far as I can see, only a few millimeters. So apparently this has failed, or has it? What I do now is I repeat my experiment, but this time I put my tube all the way down into the water, more than 6 centimeters. And now I lift it up again, put it just on the surface of the water, put my finger on the top to close it, and then I try again to see how much water has been sucked into the tube here. And I wonder if you can see it here. Honestly, I cannot. I think it's around here, which should be around 5 centimeters. So this is almost, but not quite, the 5.9 centimeters I thought I would have. So this has more or less completed the experiment. So was it a failure, or was it not? Was it okay? Well, I look back to the formula again here, and we had this cosine to the contact angle theta, which I said we had no other information, we have to guess it. And the hypothesis is that the first time you put your tube into the water, then the surfaces are a little bit hydrophobic, perhaps, such that the contact angle is not 0. It makes another angle like that. And then cosine to that theta could be 0 point something, we don't know. When the vessel has been first time completely in the water, then next time when we lift it up, then theta might come very close to 0. And if we have cosine to theta equal to 1, then we get the 5.9 centimeters. But if theta is a little bit less, then also the capillary height should be less. So I'm not sure if this was a success or a failure. That's typical for physics experiments, perhaps. But this was an attempt to show you something about capillarity and to demonstrate it in practice. Thank you for listening into this.